Okay, great. So I think we're a little bit like behind time, so I'll try to like get this done as quickly as possible. So today I'll kind of like be presenting on like a survey, or rather like I'll share a little bit about my experience with TEs. And I've been like doing TEs, I think, for the past 10 years already. That's why I call it like OTE Tales. So because of the kind of like timing that we have, I would try to give like everyone a kind of like broad overview on the different types of TE designs that we have. What are some of the trade-offs, and then we can see from there. Hopefully you can like kind of like enjoy this, and then learn a little bit more on what TEs are. So I think we have heard a lot of people talk about TEs and stuff like that. And like one of the first thing most people think of when we talk about TEs really is like Intel SGX, Intel TDX, AMD SCV. But really, in essence, or like fundamentally, what exactly is a trusted execution environment? If I have to use one word to like explain it, it's actually isolation. A TE is basically a space which is isolated from any other like entity or agents. It is protected against any outside interference or observations. So if we can achieve this isolation, then we have a TE in essence. So if I have to use more words to explain that, the difference really between all the different TEs that we see right now or in the future really is in the mechanism in which we achieve this isolation for TEs. So this is a kind of like a summary of what I have in mind on what are really the kind of like different isolation mechanisms that we have currently. We have process-based isolation mechanisms, and I think that is kind of like brought forth like an example of it is actually Intel SGX. We have VM-based, for example, Intel TDX, AMD SCV, or even ARM CCA. We have hypervisor-based isolation mechanisms. There's a group of kind of like so the first three, most people would actually heard of it before because they are like commercially available and it's really popular. When we talk about TEs, these are the type of TEs that we imagine. The next two, actually, I think is some of the more interesting kind of like directions that I think TEs can move towards. One of it is what I call design your own TE, or I can't find a better word, so I'm just going to call it design your own TE. Incidentally, this fourth type of isolation or this fourth type of TE design is actually one of the oldest. I'll kind of like go into more details later. And the last one really is you can actually achieve a TE using purely software solutions if we can guarantee that there's absolutely no physical access to the machine. What do I mean by it? We'll kind of like touch on it later. So I think I should stop like wasting time here and go straight to the first one, process-based isolation. So when we talk about process-based isolation, like the first thing that comes into mind is Intel SGX. It's like probably the most famous TE that we have, because if you ask me, it's actually the very first easy to use TE. I think a lot of people might be rolling their eyes like, what do you mean by easy to use, right? Like it's so hard to code like an enclave in Intel SGX. But you need to know that before Intel SGX, in order for you to like develop or use a trusted execution environment, you actually have to like know how to write an OS, talk to hardware device drivers, or even like build your own hardware. So like Intel SGX really is that very first commercially available TE. And the model is kind of interesting because it is very easy for us to reason about like the security of say an Intel SGX enclave, because it's actually process-based. That means what we need to reason about is that I have this program that I'm running. My program, like part of my program is untrusted, part of my program is trusted. The trusted thing is running in the enclave. And then there are well-defined like interfaces that allows me to call into this secure world. As a result of this, what we have really is that the trusted computing base, the TCB, or rather like the things that I have to trust in order for me to be confident that my trusted execution environment is secure, is relatively small. It's actually one of the smallest, if you think about it, compared to a lot of the other solutions. And the attestation process of this particular type of TEs is simple because I don't have to consider like any like trust extension. There's a process that's running in an enclave. I measure the enclave. I have confidence of what is the program that is running within this enclave. So like these are some of the benefits that we have for process-based isolation. What about the cons, you might be asking? Well, it's hard to develop for. You have to kind of like rewrite a lot of existing code because a lot of the code that we have now don't have this idea of unsafe and safe privilege kind of like separation. So in order for us to make use of like programs, we will have to rewrite the program and feed it into this particular model. There are projects like Grameen that tries to make it easier by kind of like providing library OS that shuffled like data between the trusted and untrusted world. But in general, this is where the pain point for like Intel SGX or process-based isolation TEs have. So we'll move on to the next one, which is like VM-based isolation. Like this is the shiniest new toy that we have right now. And it would probably be the future for TEs like moving forward. And why is that so? Like Intel developed Intel SGX, right? And I think one of the things that they realized is that it's really hard to use Intel SGX, so much so that you have very little people actually capable, like willing or capable to develop applications using Intel SGX. So the nice thing about this VM-based isolation really is that there is literally zero work required for developers, because the entire virtual machine is actually within a trusted domain or like a enclave itself. Developers, when they're developing their applications, can just develop it like any other normal applications. They have full access to the resources that's provided by their operating system. Like for example, if you are running a Linux virtual machine, you have access to your network sockets, you have access to your devices. It's a virtualized environment. You have your file systems, you can have different processes running in it. You can have databases that actually lives in that same enclave as your workload, which actually makes developing your workload really easy. And this is the reason why like you can just spin up a confidential VM and then you can run like Reth or Geth or Nethermind or anything that you want inside it, including like a full-blown database. So if it's really so easy to develop like applications using VM-based TEs, right? Then why is the catch? There must be a catch, right? Well, I think like there's no free lunch in the world. Like with this ease of development, you actually incur a cost on like the security side, or like how do I ensure that the workload that I'm running is indeed correct? So one of the things that we talk about, like for example, when I mentioned about Intel SGX or like process-based, I mentioned that there's a small TCB because I only need to trust the binary that's running. In a VM-based isolation kind of like mechanism, I actually have a really big TCB. What do I mean by a big TCB? I actually need to trust things like I'll call it the micro hypervisor. So in Intel TDX, there's the notion of a SIM. You can think of it as a tiny little hypervisor that Intel wrote that will handle a lot of the kind of like paging information and the hardware stuff that sets up the enclave. So I have to trust that. Then I have to trust the firmware or the BIOS, the UEFI BIOS that is running within my guest. I have to trust the operating system, which includes the kernel and the user space of my operating system. And then finally, I have to trust the workload that I'm running inside the, what's that called? The confidential VM, the VM-based TE. So now instead of just the workload that I need to trust, there's this whole huge other like baggage that I have to bring along for the ride in order for us to have this. Now, this this increased TCB, number one, it actually brings about like a higher attack surface, because I think we all know that developers write bugs, and then like the functionality is a nice side effect that comes from writing bugs. So the more code we have, the more bugs we have, and the more issues we have. So typically, if we want to run something secure, we want to kind of like minimize the amount of code that we run inside this secure domain. So that is like one of the issues of it. The other issue really is the complex attestation process that we have. If you think about it, like for Intel SGX or like process-based, we just need to verify the process. In a VM-based isolation, I actually have to verify the kind of like the firmware, the kernel boot parameters, because I can have a benign kernel, but like how I start up the kernel might introduce certain trust assumption that might break some of my trust assumption. I need to verify the kind of like execution environment that I'm in. For example, the root file system, like your system D configuration, your daemons, DHCP, what's it called? Server that is running within your operating system. So all of this measurement I have to make, and after deciding, like after making all this measurement, I have to again choose like whether do I want to do it once right at the start when I'm instantiating the virtual machine, or do I want to constantly monitor what are the changes that are made in my enclave during the execution. Because if you think about it, unlike a single process, what I have now is a virtual machine that's running an operating system. If I allow the users, or if the image that I'm running within this VM-based TE is not locked down, a user can, like, for example, SSH into this machine, and the user might be able to actually modify the state of the machine. So if that is something that I want to allow for in my TE, then I'll have to perform like dynamic measurement or dynamic attestation of my work environment. So all these are complications. What we are doing really is kind of like we are shifting the development hard work into like attestation hard work. But that being said, right, I think the nice thing about like having this kind of VM-based isolation really is, number one, I think it's more useful to have something that is easy to develop for, and then the hard work of like making sure that attestation is right can be done by a small group of people. It's just like having your compiler. Not everyone needs to know how to write a compiler or how to make sure that the compiler compiles efficient code. People just write programs. We have a small group of people that are really experts in compiler designs, build the compiler that can be used by others. So this is the reason why I kind of like think that VM-based isolation would be the way forward. The next one is like hypervisor-based. Now, this is an interesting thing. If you think about it, like one example of it is AWS's Nitro enclaves. I would actually kind of like categorize it as a transitional species, actually, between like the old what's it called, the OTE design, which will be in the next slide, and a VM-based design. So hypervisor-based isolation TEs, right, are actually VM, kind of like partial VM-based TEs. In the previous one, like in a VM-based isolation, the hypervisor is in charge of setting up this VM, but you have hardware level guarantees like memory encryption and stuff like that to protect to isolate the access to the physical to the data. For hypervisor based, if we are taking like Amazon's AWS's implementation, it can be technically considered hardware enforced because the hypervisor is actually hardware based. They have their Nitro HSM. that is responsible for separating out, assigning, for example, the PCIe lanes, the memory, and stuff like that. But there actually isn't any like hardware enforced memory encryption on the system itself. That means if I have physical access to the machine and I can probe the memory, I can actually see whatever that is executing within the trusted execution environment, within this hypervisor-based trusted execution environment. So you might be asking like, hey, then why do I even want to consider like such a TEE? Oh, sorry, I missed out one point. For AWS, Nitro Enclaves, there is also a need to kind of like rewrite your program. So the transparency, the application transparency is not like perfect because they introduced the notion of like, they would reduce, you have a VM, but you don't have a complete VM because you don't have access to some of the devices that you might expect from a VM. You have, for example, a VSOC to communicate between like a rich VM and a secure VM. So you have to rewrite it a little bit. Then you might be asking, hey, in that case, then why do I even want to consider like this kind of hypervisor-based solutions instead of going straight for the VM-based solution? The nice thing about this is that if you can live with the fact that one, you will lose certain guarantees on the, what's it called, on the isolation that you have. Two, in the case where I can trust the physical, what's it called, access of the machine is being kind of like enforced, then the hypervisor-based solution actually allow us to very quickly modify any standard kind of like machine that we have into a machine that is capable of TEE. That means, for example, I can make use of, let's say, Amazon decides to sell their HSM, which is highly unlikely. But let's say if they do, I can get the HSM, I can put it into, let's say, my Ryzen computer, and I can actually make it TEE capable because the hypervisor is actually the one that is responsible for carving out the enclave. So basically, this is kind of like hypervisor-based isolation. Then you might be saying like, hey, the hypervisor-based TEEs are like a transitional species, right? Then what is that species that come before hypervisor-based TEEs? I call this the design your own TEE because like this is basically how we built TEEs back then in the good old days. One of the actually very first kind of like commercially available platforms that we can play around with is actually ArmTrustZone. The thing about ArmTrustZone is that the idea is very simple. You have one hardware, but we allow the user to kind of like split the hardware or like transition the hardware between a trusted world and an untrusted world. So you can think of it as I have a hardware that supports one single VM. Like you don't really call it a VM because it's running on the actual hardware. So I can run some code in the untrusted, like on a normal ARM platform, and then I can toggle some instructions, or I can call into something called a secure monitor, where it would transition the entire hardware platform that I have into this secure world. So that there won't be any more unsecure code that is operating in that domain. So the thing about like ArmTrustZone is that it's the first that we have, and we are still using it. So there are a lot of examples of ArmTrustZone kind of like designs that we have. For example, like Samsung Knox. If you have a Samsung phone, actually you're running a TEE inside your phone. So Samsung has this service called Knox. Some cloud providers make use of TrustZone to provide TEE functionalities like Huawei Cloud, Ali Cloud. Yeah, that's the two that I can remember off the top of my head. There's also an open source. So what's the problem with this kind of like TEE, right? The thing is, you previously, when we talk about Intel SGX, Intel TDX, AMD SCV, AWS, that is actually a prescribed trusted execution environment design. That means the manufacturer would be the one that would design what is the attestation workflow. The manufacturer would be the one that would be implanting the kind of like the root of trust, the secret that is in all the devices. The manufacturer would determine how you would kind of like make use of the TEEs to perform computation. What are some of the guarantees? For Trust Zone, what they do really is that they provide you with tools. Like I said, it's a kind of like hardware toolbox that you have such that you can build your own TEE, which means there's no attestation workflow for ARM Trust Zone devices. The person that will be developing the TEE would be the one responsible for kind of like developing the attestation workflow. There are no secrets that are embedded in the so-called the Trust Zone hardware. So secrets must be separately embedded into the hardware device itself. Whether you want to make use of eFuses or embed it into some EEPROM or some flash once memory, it depends on again the manufacturer. So this actually makes it really complex because you have to write, for example, a secure operating system for your TEE. You have to design your own attestation workflow, infuse or embed your own secrets. And then you might be asking, what do I gain by doing all of this? There's one thing that Trust Zone does that all the other TEE solutions doesn't, which is secure input-output. Because you have control over the hardware and you are kind of like provisioning all the hardware, you can actually ensure a kind of like secure chain from your sensors, for example, your keyboard, your monitor, your touchscreen, all the way to your enclave. For all the other solutions, you actually don't have that guarantee. You have to trust that you basically have to assume that all inputs that you are receiving is untrusted. And then you kind of like build in the trust by using like Diffie-Hellman key exchange schemes to make sure that it's end-to-end encrypted and the source is trusted, blah, blah, blah. But in the kind of like design your own TEE, build your own TEE paradigm, you can actually have trusted IO. And trusted IO is extremely important when we think about using TEEs for like provenance. Like, for example, I use a camera to take a picture. How do I prove that this picture indeed comes from the camera instead of some AI-generated image? I can actually make use of this secure input-output channel to do this. So this is basically Trust Zone. If you kind of like extend it further, secure elements in like I think the previous presenter talked about like Java cards is one such design your own TEE kind of mechanism. Again, the Java card just provides you hardware-assisted isolation. The rest, you design it yourself. There's actually a recent paper this year in Asia CCS that's called Build Your Own TEE. They kind of like propose the idea of combining both hardware, like your ARM or your x86 CPU, and with a FPGA. So the idea is that you can use your kind of like generic CPU for high performance untrusted execution, and then you design specialized TEEs as like co-processor to your untrusted world. So I think that itself it's really a direction which we might want to go into. And finally, if we kind of like push the idea all the way, if a TEE just means isolation, then really we can achieve a TEE using just a pure software plus physical isolation thing. So instead of trying to make use of hardware or cryptography to try and hide the data or access to the hardware, we'll just take the hardware and then send it up to space where no one can actually touch it, or we seal the hardware and like dump it into the ocean. Like I think Microsoft actually dumped the entire data center into the ocean. It's called Project Netwick or something like that. We can actually do that. So if you are able to stop all physical access from the actual device itself, then we can enforce control through purely software means, which means that any standard computers, like any standard machine that we have, can be turned into a TEE using just a pure software approach. And then we have the benefit of like not having to worry about like hardware probing attack, those kind of voltage injection attack, physical side channel attacks, and stuff like that. So I think this is really, really, really interesting. And it kind of like shift the idea of what a TEE is. Like, do we really need to have specialized hardware to do TEE? Can our phone be used as a TEE? We lose certain guarantees on, like, for example, memory encryption. But for example, Google Play integrity allow us to enforce that, hey, we are running in an untempered environment. That might be good enough for certain use cases. The same for Apple phones. So I wanted to kind of like talk a little bit on like security, but I think I'm a little bit out of time, so I'll just kind of like zoom past it. In terms of hardware security, I think printers have this awesome thread on like physical security. And then there's also this ZTE article about the supply chain and stuff like that. So I don't think I can do a better job than them. So I'll refer you to them for this articles. What I want to focus on really is on the software side of things, because if we think about like TEE, other than the hardware component, there's also the software component. And if we think about like physically isolating the machine, then what we have is just software security. So if we think about it, like there are kind of like two big parts that I'm kind of like interested in. One is the supply chain of your software that you're running. So what we need to do is to ensure provenance and integrity. And then I think Poetic did a presentation just now also on like reproducible builds using Grix. We also develop a kind of like a testable build using TE build. So there's kind of like two ways on how we can ensure that our software supply chain is indeed what we think it is. The other kind of like issue that is sticking up for TEs are really side channels. And side channels are, one, really, really evil and really, really hard to fix. They are, what do I mean by evil? They are really subtle, because things that you might think that there isn't any side channels, like for example, I can use constant time algorithm, but if I use a mem copy somewhere, the mem copy itself might actually not be constant time, and that would introduce a side channel element. You can have cases where accessing the cache would result in a side channel leakage. So side channels are really hard to prevent, and they are even harder to fix. There are some papers that I listed here. One of it is actually on side channel attack called a pigeonhole attack, which makes use of page faults to kind of like retrieve the secret key used for cryptographic cryptographic operations. And the other one is really like, what are the different kinds of side channel kind of like mechanisms, and how, when we try and stop side channel, for example, if I try to stop a timing side channel, it might result in an ordering, like an execution side channel. Or if I try to stop a memory access side channel, I might introduce like timing side channel. So I think that is something that we have to kind of like think about and identify ways on how we can work around it. So there is actually a technique called ORAM, oblivious RAM. It's a really good technique to kind of like make use of to make memory access oblivious. Because if you think about it, in order for us to stop side channel attacks, we can either, one, make it deterministic. So everything looks the same and I can't tell anything. The other way really is to have like randomization, so that given a certain budget that I have, the attacker won't be able to tell anything. And then before this budget is used up, I will re-randomize everything. So basically, that's it. I don't think there will be any questions, so thank you for your time.